over another. So we're going to start with problem number 1. So with problem number 1, it says the rate at which rainwater flows into a drain pipe is modeled by this function r. In cubic feet per hour, t is measured in hours, and we have a domain here. It says the pipe is partially blocked, so water flows out of this drain at a slightly different rate, and there are 30 cubic feet of water in the pipe at time t equals 0. So this 30 feet is going to become important later on. We're going to get to that in just a bit. Part A says how many cubic feet of rainwater flow into the pipe during the 8-hour time interval. So I have this rate here, r of t, and this is the rate at which water is coming in. So if I want to figure out the total amount of water that's come in over 8 hours, then on part A, what I want to do is find the integral from 0 to 8 of r of t dt. So I want to find the, let me get to my calculator mode. So I want to do the integral of, this is going to be 20 times the sine of t squared divided by 35. And I'm going to be integrating with respect to t from 0 to 8. And this will give me my answer, which is 76.570. And because they've been giving us units here, cubic feet per hour, and hours, cubic feet are our units for our volume here, and the units are going to be very important. So what the AP has typically done is if you fail to put units on one of your answers, you're going to lose a point for that, and then anytime that you lose that point, you're not going to be penalized again for it. But units are very important in this problem. So we're probably looking at 1 point for setting up the integral and 1 point for the value. This is what they've typically done. Again, I'm not an AP reader, but this is what we've seen on typical problems in the past, and so I would expect them to follow a similar practice here. For part B, it says that the amount of water in the pipe increasing or decreasing at time t equals 3 hours, and it wants us to give a reason for our answer. Keep in mind that water is being added at this rate, and water is being subtracted at this rate. So if I want to find the change in water with respect to time, it's going to end up being r at that particular time minus d at that particular time. So the change in water when time equals 3 is going to be r of 3 minus d of 3. And so if I evaluate that, I need to substitute 3 into this equation that we just had. So I'm going to backspace up, and I'm going to stick 3's in here. So 3 squared. And then I want to subtract this quantity, and this quantity is my d of t. So this is going to be negative 0.04 t cubed, but it's not t, it's 3. So it's going to be 3 cubed plus 0.4 times 3 squared plus 0.96 t, well not t, 3. And my parentheses are closed, so when I calculate this, we end up with this w prime being equal to, excuse me, let me get my calculator back up, being equal to 0.313 negative. And they'll accept credit for either the 0.313 or the negative 0.314. When the rounding occurs in this last spot, they'll usually give you credit for either or both of them. So don't worry so much about that. If you wanted to leave your answer as negative 0.3136, that would be fine. It gets rid of the ambiguity there. But what's important is that this is a rate, so this is cubic feet per hour. So it is going to be important for me to put those units on there. Then we get part C, and it says, at what time t, 0 less than t less than 8, is the amount of water in the pipe a minimum? Justify your answer. So I need to remember that minima occur at critical points and boundary points. So my boundary points are going to be at t equals 0 and at t equals 8. For my critical points, I want to know where w prime is equal to 0. And I need to figure out where those points are going to be. So I'm actually going to jump to my graphing part of this. I'm going to put y equals, and I'm going to type in my first equation, which is going to be 20 times the sine of, in this case, x squared, because I'm graphing y as a function of x, divided by 35 for my first function. I'm going to set up my second function to be the negative 0.04x cubed plus 0.4x squared plus 0.96x. And I want to know where these graphs intersect on my domain. Remember, my domain is from 0 to 8. And so if I graph this, so I see that something happens here at 0. I think I did something wrong here. Let me make sure I didn't do something wrong here, because that's not what the graph should look like. So give me my y equals. Okay. And actually, this intersection point is what I'm looking for right here. So I'm going to go math, so F5, and I want to figure out where the intersection is. And my first curve is that one, my second curve is that one, and that's my lower bound is going to be somewhere around 2, upper bound somewhere around 4. And so I find out that they intersect at 3.217. And the issue here is that it looks like they may intersect over here. So graphing these two lines may not be the best way to do it. What I may want to do is I may want to go ahead and let me actually cut this and then go up to my equation 1 and paste this. So minus this equation, paste, and have that be it. So this is really my r minus d that I'm dealing with. And if I graph this, then I can see, okay, it's decreasing on this interval, and then it reaches this intersection point here, somewhere between 3 and 4, and then this is increasing, and it tapers off, but it never actually, the derivative is never 0 again. So I'm going to go ahead and I'm going to go ahead F5 and find the intersection somewhere between 3 and 4. And I'll end up getting that exact same 3.27166. So this is going to happen at t equals 3.27166. So what I need to do is I need to figure out the volume of water at 0, the volume of water at 3.27166, and I need to figure out the volume of water at 8. Keep in mind that normally what I would do is I would be integrating from 0 to whatever time I'm dealing with of this r of t minus d of t with respect to t. And then whatever I get, I would have to add the 30 cubic feet that we started with at the beginning. Of course, here, this is just 30, because this integral is going to be 0. Here I'm going to have 30 plus the integral from 0 to 3.272 of r of t minus d of t. And when I put this in my calculator, going back to my home screen, I'm going to take this function and I want to take 30 plus the integral of this, and it's going to be all of this with t's instead of 3's. Would have been helpful if I'd changed these along the way. But I'm going to integrate this from 0 to that r value. And I'm actually going to put in all the decimal places that we got instead of just the 3 decimal places, just to make sure that my answer is as accurate as possible. So I'm going to integrate this with respect to t from 0 to 3.27166. And after a few minutes of repose, we get our answer of 27. And notice that this is significantly less than the 30 cubic feet that we had here. And then I need to evaluate this as at 8, so I'm going to take a step back and just delete this back up to an 8. And when we do that, we're going to get this 30 plus the integral from 0 to 8 of r of t minus d of t dt, which is going to be 48.544. And so we have a minimum of 27.965 cubic feet at time equals 3.272 hours. And so that's what I'm looking for the solution. My justification is that critical points and boundary points are the only places where extrema have, and this is the smallest value of our 3. So I'm showing my work here to kind of explain what's going on. And then part D says the pipe can hold 50 cubic feet of water before overflowing. For T greater than 8, water continues to flow into and out of the pipe at the rates given until the pipe begins to overflow. Write but do not solve an equation involving one or more integrals that gives the time W when the pipe will begin to overflow. So we've got this formula here that 30 plus the integral from 0 to whatever our time is of R of t minus d of t dt is going to be the amount of volume that we have. And whenever this volume hits 50, that's going to be the threshold point. Remember that when we were looking, when we were looking at our graph, we noticed that let me go to our graph real quick. Our graph, this was positive, so this increase that we've got over here, the area of this means that we possibly could get up to 50 pretty quick. Remember that when we were at W of 8, we were at 48.544, and our derivative is still positive. So we're going to be continuing to add, and so we're probably going to hit that 50 threshold for this W. So I kind of stopped talking about the points. Let me go back to it. 2 points for part A. Down here, you're going to need some type of representation for the amount of water with respect to time, and you're going to need to have your answer for what happens at time t equals 3. You're going to have to identify some points, like the t equals 0, the t equals 8, the t equals 3.271, and you're going to be looking at a point to justify which one of these is your smallest. And then for this expression, you're going to have probably 1 point for this integral here and 1 point for finishing it out, writing it out as a equation. So this is probably where your 9 points are going to fall. Again, the one global point where if any point along the path you kind of messed up your units, then you're going to lose that point, but everything else should be fine.